Okay, so welcome to what is a mini course within our course, and what we're going to be talking about here, we wrote it up as well, is multicolor Ramsey numbers. We've seen, or lots of you have seen at various moments, results about Ramsey theory, about Ramsey numbers. We're going to try and focus a little bit more on multicolor Ramsey numbers, and in particular, a recent paper which went on the archive last week, which gives an exponential improvement on the upper bound. And that will be the main focus of this sort of mini course. But let me give the quick overview of the plan for the course. So today, we'll talk about lower bounds. On Thursday, which is the next class, we will talk about sort of the upper bounds, particularly in the two-color case, that we already know, and discuss the difficulties with generalizing to more colors, at least with the types of proofs we had before. And I don't know exactly how many classes there'll be afterwards, we'll see how we go, but basically in a week or two afterwards, we'll present the new upper bound, or new proof of the upper bound, which does generalize to more colors. This is the paper that went up with 8 authors. Don't worry, we name everybody when we get to it, but we will discuss this in the 2 weeks afterwards. So what we're going to do today, as I said, the main focus will be lower bounds. I actually have some slides that I've used for some talks. So I think perhaps first we'll run through those slides to give a general introduction to Ramsey theory and some discussion of lower bounds as well, in general. Then after that, I don't know if that'll be 20 minutes or half an hour or something. After that, we will focus on the particular problem of lower bounds for multicolor Ramsey numbers. And we'll see some other recent results from recent in the sense of being from the last 5 years. Okay, so now I'm going to go to slides for a little bit. Very good. But I guess on the video, we'll just share directly the slides. So here we go. This is a nice AI-generated image, perhaps, of what might be a multi-colored graph, although it's a bit messy. And yes, that as well. Right. So let's talk through this presentation first, as we said. So the first thing you might ask is, what is Ramsey theory? Ramsey theory is the study of inevitable structure. There's all sorts of different situations in which you're looking at a object, and if you take it large enough, you will inevitably find structure within it. The type of structure depends on the situation. And this occurs in number theory, additive number theory. This occurs in geometric situations, subspaces, Euclidean Ramsey theory. There are sort of a whole myriad, a great variety of applications of this. And I sort of mention these because I feel it's a shame we can't really dive in to do everything. So really, this slide is an apology for the fact that we're really going to concentrate on a much smaller group of problems, particularly graph Ramsey theory, where you're colouring the edges of a graph, and particularly graph Ramsey theory, where you're looking for cliques. So that would be our focus. But it's just to mention Ramsey theory is a very much more general thing. Ramsey, of course, was a philosopher. He studied economics and mathematics as well, or philosophy, economics, and mathematics, made huge contributions to all three, despite the fact that he then died at only 26 years old. And he said things like, I hope you like red, blue colouring. So I think that's an exact quote. His theorem at the time was about if you do a red-blue colouring of all the pairs of the integers, then you can find an infinite set where all the pairs in there are monochromatic. And he needed this for a particular application in logic. But many people, and in particular Erdos and Sekeres, decided that an interesting thing to focus on with respect to this problem is the quantitative behavior. Suppose I want a clique of a certain size, how many vertices do I need to start with in order that I can guarantee that much structure in there? The definition we put up here is actually what you call the, well, you could say it's off diagonal, or it's the general definition, where you might want something different in each of the two colours. So our KL is the smallest n, such that every red-blue colouring of Kn, or the edge of Kn, contains a red clique on K vertices or a blue clique on L vertices. And it follows from Ramsey's result that this is always finite, using Ramsey's result and a compactness argument. Erdos and Sekeres gave the first sort of effective upper bound, which is 2k choose k. Okay, technically you can put -1, -2 or something like this, but we're going to be thinking about improving things by much bigger factors than that. So it's nice just to have this form of their upper bound. And this is smaller than 40k, it's sort of 40k over root k. But again, because we're going to be interested in bigger improvements, in a sense, you can think of it's roughly 40. On the other side, up for a while, people didn't have any good way to construct graphs that would not have large cliques in one or the other color. And Erdos managed to do that and use the random coloring to prove that if you have just root 2 to the k vertices, that is not enough to guarantee a clique of size k, one and two colors. So now let's go into a bit of discussion of lower bounds. In a sense, our object today is discussion of lower bounds. Because I have these slides ready, we're going to first do a general discussion, and a bit later, when we go on the board, really, we'll have a discussion in depth on the multicolor. So this first discussion is a bit more just a general lower bound discussion for Ramsey. So even just what is the challenge, what is the objective? If you want to prove a lower bound on Ramsey numbers, you need to say a certain number of vertices is not enough to guarantee the structure. How do you do that? Well, you need to exhibit a colouring of the edges of the complete graph with some n, so that you do not have a red, say a red KK or a blue KI. And over history, the history of the subject, there have been many different ways in which people have done this. And this is a simplification, but let's mention 5 such ways. It may be random, like Erdős's first construction for the lower bound of RKK. Just a pure random colour. It may be what I call random star, which means it's random, but somehow you've changed the distribution. So we'll mention examples in a minute. You can do something random, and then you're not happy with the result, so you come in and mess around with the results. You change the result. So in a way, what you did is a random step and then a deterministic step. This is perhaps the most interesting one to mention now, is deterministic plus random. As we'll see, this has had many applications recently, including one we'll mention here in the slides, and it's also behind the ideas we'll discuss in multicolor Ramsey numbers today. And finally, there are some constructions that are purely deterministic. Let's give a quick example for each of these, just so you have a good sense of what these types of examples are. Well, first random example is Airbrush's lower bound on RKK. You colour each edge randomly, red or blue with probability of half, independently, and you let X be the number of monochromatic cliques of size K. If the expected number of cliques is less than 1, so for a certain range of n up to a certain value, then you can colour without a monochromatic KK, right? Because if the expected number of monochromatic cliques is less than 1, there has to exist a colouring without it. There are many problems where you use this random start approach. You do something random, but you use a different distribution. And some off-diagonal Ramsey problems in particular, you might want to take a random graph which is specifically avoiding a certain type of subgraph. Well, you just implement that process. You add edges one at a time at random, but with a rule that they do not complete a certain type of subgraph. We studied the triangle-free process, K4 free process. So for any small graph H, you can do the random process which avoids that H. So random plus deterministic is alteration. This is one famous, it's a section in Allen and Spencer book, for example. It's often random, does something a little bit silly, and you can just come along and sort it out afterwards, or remove some vertices, or recolor some edges, mess around a bit with the results, and improve your balance. Let's jump to the last one, deterministic. Purely deterministic constructions exist. For example, for R44, you can do a colouring using quadratic residues modulo 17. This is a funny construction that happens to work in that case. And there are lots of other graph Ramsey problems where it's not two cliques, like a clique versus a path, where the best construction is a Turan type of colouring. Colour inside parts in one colour and you colour between parts in another. And that's a very deterministic construction. But as I was saying, probably the most promising for future improvements is this deterministic plus random. So we'll mention one instance of it here in the slides, and then, as I say, the rest of the lecture will also be mentioning other examples that are related to this idea. So last year, Mateusz and Verstraete managed to improve on our 4K. So this is how many verses you need to get just a clique of 4 verses in one color, or a clique of K verses in the other. K, obviously, we think of as being very large. We think about the limits as K goes to infinity. Yet in the other color, you have to avoid something very small. Previously, the lower bound was around K to the 5/2, K to the 2.5. I think the best bound at that point was given by probably Bowman and Kivash with an H-free process, which gave the best lower bounds for lots of these things. And it's interesting to test. I mean, I think for a while, I in particular had the intuition those types of processes were probably giving you the best kind of behavior you should be able to get. And so it's quite surprising, to me at least, that they managed to produce a much larger colouring that still avoids K4 in one colour, KK in the other. Yes, this symbol, which is like a theta with a little tilde, just means up to logarithmic terms. Okay. So up to, so maybe you could say, in particular, what they proved is at least k to the cubed over log k to some power. Maybe it was 4 or something.
Alteration is only a version.
Alterations, yeah, I don't remember exactly what alterations gives. It tends to be quite difficult to do alterations because you need to put a very low probability in order to not have many K4s. Therefore, it becomes very sparse. And it probably is maybe it would be K to the 5 over 2 as well. Maybe it's just worse in terms of the log factors. It's probably just worse log factors compared to the Bowman cube measurement. But still, and this is the correct order, yes, the correct order of the upper bound already existed. So it was really closing the gap a lot to go by closing by a whole root k. In some sense, their argument is deterministic and then 2 random steps. We'll describe this argument fairly informally just in these slides. It would be lovely to give a whole talk just on this because it's a lovely result as well, but that's not going to be our focus. So they use something deterministic, which is use projective planes to define a certain graph. That graph is a union of cliques that have a particular significance from the point of view of the projected plane. And I think maybe another algebraic structure that they have related to that projected plane. And by doing so, they can have a graph which is a union of cliques, but in such a way that the only K4s in this graph are contained in those cliques. So now you could think, I want to color all of these edges in these cliques, I don't know, blue or something. You'd be doing quite well, except you may have lots of K4s, you may have some number of K4s, well, lots of K4s in these cliques. What you then do is you replace each of these maximal cliques with a uniformly chosen complete bipartite subgraph. Obviously, then that kills all the K4s. Now, you may still have large independent sets. But they do an extra level of randomness, which is they say, we're not going to go straight to having 0 independent sets of size k. We'll start by just counting how many independent sets of size k there are, which is more work, of course, you need to go and do the calculations. But if they get a decent bound on that, they then take a random induced subgraph. They zoom in to a small part of the world, and if you get the numbers right, you can do it in such a way that it's unlikely that any large independent set of size k is contained in this little subset first. And they managed to do it in such a way that this subset is still large enough to give you the lower bound you want. We'll see similar ideas in a way today, although luckily, in a sense, we'll be in a slightly simpler setting than these projected planes, which will make it slightly easier to explain the ideas. Right. Just mention a related problem related to the Matthäus-Westrite's approach. They basically use at the end of their argument a certain graph container lemma, which enables them to say, because we came up with a K4 free graph that is quite dense and remains fairly dense, even in smallish sets, even when you look in smallish sets. And from that result, you can basically deduce the counts on the number of independent sets, and you can deduce the bound you want on the Ramsey bounds. So what will be interesting is to generalize that to larger cliques instead of K4 to K5s. And let's have a definition. given a graph with density beta, for some beta, let's say G is dense on R sets of size R, if when you restrict G to any set of size R, the density there is at least a tenth of the original density. It's a slightly arbitrary definition the way I've done it, but it gives you the idea. So you're dense on root n sets, if whenever you zoom into root n vertices, the density within those is still a tenth of the original density. And basically what you want to do is for S at least 5, you want to find, so I'll put it as a question, does there exist a KS3 graph G with the number of edges being n to the 2 minus 1 over S, a function of S obviously, which is dense on sets of size root n. So we don't need to go through the details, but if you can find such constructions, such graphs, you can use these. I mean, if I've done the calculations correctly, I just worked out what you should need. You can use their approach to, or this general approach really of using counting the number of independent sets, using the graph regularity stuff, and you can use it to make a new lower bound on those Ramsey. Right, so finally we get to the subject which is our main focus, will be our main focus through the next lectures, which is multicolor Ramsey numbers. So the so-called sort of diagonal case, when you're looking for the same size clique in any of the colors, would be like this. That will have R colors, so you don't just have red and blue, you might have red and blue and green if R is 3, or red and blue and green and yellow if R is 4. And so this first diagonal one would be what's the smallest n, such in every coloring of Kn with R colors, I can guarantee a monochromatic clique of size K. So it's the same idea, it's just now instead of 2 colors, instead of a red-blue coloring, it's R colors. Of course, more generally, you could write out a definition for R of K1 up to KR, in which you want to find the sum I, a clique of size Ki in color I. Right? Clique of size K1 in color 1, or clique of size K2 in color 2, etc. If you do this, then actually you can get a bound, an upper bound, on this quantity exactly following the same Edwards-Sekresh argument that they used for 2 colors, and it gives you, instead of that binomial upper bound, K plus L choose K, it gives you the multinomial coefficients as an upper bound. So the Ramsey number of K1 up to KR is at most sum the Ks and do the multinomial coefficient with all of those Ks below, which is the same as the number of ways to divide a set of size K1 up to KR into R subsets of those respective sizes. Okay, again, there's this way where maybe you can have -1s on the bottom, but that's not really our focus. In particular, if you think about the diagonal case, then you can put all the K's equal, and you have an upper bound which is RK, choose, you say choose multinomial? Anyway, K on the bottom. And again, just in the same way that the usual Ramsey upper bound is just a polynomial factor away from 4 to the K, this bound is just a polynomial factor away from R to the RK. I should say we'll mostly think about the case where you have a fixed number of colors, 3 colors, 4 colors, 5 colors, and you let K go to infinity. At least that will be our focus. There are nice problems where you say, I'm only interested in finding a triangle, or in other words, K will always be 3, and you think about the behavior as R goes. that won't really be our focus. So in general, if I make comments like this is correct up to a polynomial factor, I always mean that we've fixed R and we're thinking about behavior as K goes. Right, so that is the situation. Well, this basically was the situation until very recently. It's worth mentioning with respect to the upper bounds that until recently, there had basically been no improvement on this upper bound, except maybe by a constant factor. Maybe you could divide by a constant, but this is, you know, it's different from the two-color Ramsey number. We'll discuss this more in the next class, but in the two-color Ramsey number, there were a sequence of improvements. How we can divide by root k, we can divide by a super polynomial factor, working their way up. Whereas here, the only improvements, I think, have been by constant factors. Okay, but the subject of today is the lower bounds. So let's think about the lower bounds of these guys. If you take the airbrush random coloring from 1947, we know it's exactly the same argument. If the expected number monochromatic cliques is less than 1, then you have a chance of being lucky and your coloring has 0. And so you just do that same coloring, but randomly with R colors instead of 2 colors. And it gives you the lower bound, which is R to the K over 2. The same way as 2 colors includes the case 2 colors 2 to K over 2. And one way you can improve on this is actually the observation of Advert, which is basically if you can color using R1 colors, color a graph with N1 vertices, and with R2 colors, because this Ramsey number -1 is basically a number of vertices that you can color, right? Two positive. If you can color N1 vertices with R1 colors and not have a clique, and you can color N2 vertices with R2 colors and not have a clique, okay, then if you have R1 plus R2 colors, you can color a number of vertices, which is the product. And it's exactly using a product color. You basically think of the product as like, I guess it'd be like a rectangle of points or something. And basically, if they differ in the first coordinate, then you just color them according to the coloring or in that direction of the N1 points. And if not, then they're the same in that coordinate. You color according to the second color. And you can check the details in this works. And it immediately actually enables you to sort of bootstrap the airbrush random construction, and it works better for any R at least 5. The one consequence I put here, for example, it happens that the three coloring Ramsey bound is fairly good. Well, 3 is the K2. And it means if I take any R which is a multiple of 3, I can just apply Abbott a bunch of times, and it gives me a lower bound which is 3 to the RK over 6. Now it's easy to see this is better than the airbrush bound if R is, say, a large constant, because you prefer to have R in the power rather than, well, this is kind of like having log R in the power. Okay, log R. And the other thing which is good about this, if you think of R as kind of as a constant, then the lower bound is constant to the RK, and the upper bound is R to the RK. They're not so different. Right. And until recently, this was all that was known. So, well, it was in 2020, I think, in the archive, 2021 in the journal. Conlon and further managed to really come up with some new ideas, which gives you a lower bound that for the 3 color case, it gives you 2 to the 7k of rays minus kilo k. They did do some other numbers as well, but I'm going to particularly state the 3 color case because I think it's the one, yeah, it's most worth highlighting here. Wigderson, I think was in some way inspired by the ideas of Condon and Ferber, because soon afterwards he came up with a variation of their ideas, which allows you to prove, okay, it looks like a bit of a mess, but the final thing is you basically got 3rk over 8 minus k over 4. Basically, when k is larger, this is giving you a better bound than the Abbott's. Even if you use Abbott's with the new Condon Ferber bound, it's because you can obviously once you've got a better bound here, it gives you a better bound for all larger R using Abbott. But even so, Wigderson's bound is an improvement.
And does to use the only random arguments or?
Right, so these 2 results, as we're actually going to do today, use a combination of algebraic properties of Z2 to the D and randomness. So it's another example of deterministic plus random. What's interesting is soon afterwards, Solwyn proved a slight improvement on Wigderson's results. And strangely, yeah, he comes back to doing a completely random approach. Although it's not your old-fashioned Erdos, just do random. It's kind of random plus random in a way that was inspired by the deterministic plus random of the previous 2 results. So it's sort of, there's an irony that you end up back with something which is much more random again, but somehow you only arrive there via the inspiration of these results that use more structure. So I think this is a good moment maybe to move to the board. So, well, the objective today will be to prove this Condon-Ferber bound and this Wigderson bound. And we'll see how we do in terms of time. Before we get into the details, which look like Ramsey theory, we're going to do a bit of background on linear algebra in Z2 to the D. Because these constructions rely on certain properties which are not so obvious if you don't know them. So it could be useful to do that first. In particular, from the point of view of the video, we could what's going on? Right. Good. I think now they are back in the room. So it's a bit tricky this. I did that just go up. Good. And perhaps I should. Okay, so let's see what we're going to do and what we're going to say about the Condon-Ferber approach, and in particular, linear algebra in Z2 to the D. So let me put up linear algebra. Use the other pen. Z2 to D. I wonder if this is. Yeah. I need help. Okay. Yeah, a lot of people write F2 instead of Z2, and they're probably right because you should think of it as a field or something. I like Z. Good. So let's work as follows. Let's first remind ourselves what are the elements. I guess you could say elements or vectors, if you like. This would be 0, 1 sequences of length n. N equals D. Great, thank you. There's a sum, which is just summing modulo 2. All right. Maybe I won't even use the vector. X plus y, and you basically sum modulo 2, so 1 plus 1 equals 0. And there's an inner product. So the inner product of x and y, it's what you think, it's just the sum overall coordinates of xi, yi. Really, what this means is you get 1 whenever they are both equal to 1. Otherwise, you get 0, right? The other 3 cases, you get 0. So in some cases, or another way of thinking of Z2 to the D is kind of, you can do a bijection with the power set 1 up to D, right? A in the power set D, in other words, a subset of D, and it kind of corresponds to its indicator function. Basically saying where are the ones in this vector. You have a vector like D, you can say where are the ones, that's a set. And if you like to, well, sometimes it's useful to think in that language. If you think in that language, the sum is the same as symmetric difference, right? And the inner product is basically the size of the intersection of sets. But taken 1, 2. So even intersection gives you 0, and odd intersection gives you 1. One particular subset, in fact, it's a subspace, the subset of Z2 to D, which is very important for Conlon and Ferber, is the set of X in Z2 to D. So now that you have the inner product is modulo 2, you have points whose inner product with themselves is 0. It's basically any vector with an even number of ones. So this V is really the points with an even number of ones. Or in the language of sets, it's the sets of even size. I've seen that people call this property of having inner product with yourself 0 isotropic, which seems like a fancy name. It's kind of like even in a sense, but maybe we can say isotropic. We can be fancy. So once you have this fancy word, then you can think about what does it mean for a set if not only do the guys have inner product 0 with themselves, but every pair in the set has this property. So this would be useful too. You can say A is totally isotropic if the inner product of x and y is 0 for every pair x and y in M. I mean, I kind of half think you could just call this the even property, because we kind of know that 0 corresponds to evenness. For example, having an even number of elements, the set of ones being an even intersection. So if you don't like this name, every time I say it, just think it's the even property. And just because the other, if they're odd, there's not a fancy name that I know of. So if it's odd, I'm going to call it the odd property. Okay, let's say B has.
Its definition is the same as A is contained in A vector.
Yes, so totally isotropic is the same as A is contained in the perpendicular. And the other property is B has the odd property if you have in a product one, whenever you're different from X and Y, the X, Y are different. Because we're going to be particularly interested in subsets of V or what working inside V. So maybe if V has the odd property in V, vertices themselves or vectors themselves may have a product 0, even isotropic. But if you take two different vectors, we want the answer to be 1. Now, let's start with a lemma, which discuss all these properties in a nice way and will be very useful to us for the colorings later. So I guess you could call it lemma 1.1, properties of V. So the first is that V itself is a subspace of dimension D minus 1. Second, if A contained in V is totally isotropic, so it has this even property, then A is contained in a subspace of dimension at most D over 2. So in some sense you have to be small to be an isotropic subspace. And C, perhaps even more surprising, if B contained in V is odd or has the odd property, then B actually can have at most D minus 1 elements. So this is sort of related to the odd term problem, if anyone's heard of that, which is discussing how many even sets can all have odd intersection. And there's also results about how many odd sets can have even intersection. And so you can have a look online about that if you want to see more details. Right. Let's mention, yes, perpendicular spaces will be useful. It's all about perpendicular spaces. So if you have a subspace, W contained in V is a subspace, then you define W perp to be the set of X, I guess we're looking still at Z2 to the N, Z2 to the B, such that they are orthogonal to every, when product 0, with every W and W. And fact, W perp is also a subspace, and the sum of the dimensions of W and its orthogonal subspace is equal to the dimension of the space. So these are facts from linear algebra that we can use. In fact, this fact makes part A very easy because being in V basically just corresponds to having an even number of ones. And having an even number of ones means you're going to be orthogonal to the vector which is all ones, right? Because your intersection with that guy is even. Basically, have one if one is even. So actually, I'll just say one is sort of, well, it's not really trivial because it depends on this information about the perpendicular. But if you have this information about the perpendicular subspace and then the dimensions sum to D, then this is sort of trivial because V is just the orthogonal space of the 0 vector and the 1 vector. Okay. So this is a one-dimensional subspace, and V is the orthogonal space to it. So by this linear algebra facts, we know that V is a subspace and it has dimension V minus 1. So let's go to B. If A is totally isotropic, then A is contained in a subspace of dimension a most dn2. So you could just say let S be the subspace generated by A. In other words, you take all possible sums of elements of A, repeat how many times you like, eventually you stop, and when you stop, it has to be a subspace. And it's easy to check that this totally isotropic property carries over from A to the subspace it generates. Because if I have like X and Y in A, Z in A, I do a sum X plus Y, well, X plus Y still has inner product 0 Z. Right? So it's not a difficult thing to check, but it follows that S is still totally isotropic. It's easy to check. So now, actually, this is what Bruno mentioned a minute ago. The property of being totally isotropic is the same as saying that S, or the set, is contained in its perpendicular. As S, well, let's just say thus. Thus, S is contained in S perpendicular. And so, well, I could say twice the dimension of S is less than or equal to the dimension of S plus the dimension of S per. And this is famously equal to D. And so, of course, the dimension of S is the most given. A and B are done. C is maybe a little bit more difficult, so maybe I'll clear the board here and we can do C. Okay, so B has the odd property, then B has the most E minus 1 elements. So let's suppose for contradiction, suppose B has elements, and I'll just list D elements, so more than D minus 1, has elements x1 up to xd. Well, what's the first thing we can say if you have D elements of B? Well, then you have D elements in B, but it's living in a subspace of dimension D minus 1. So they're linearly dependent. Okay, so as B is contained in B, these must be linearly dependent. Linearly dependent. Usually, when you do linearly dependent, you have a sum with weights adds up to 0, right? Here, weights don't matter. Well, the weight can be 0 or 1. So really, if x is linearly dependent, it means there's a subset of them that add up to 0. So there exists I, a subset of D. Well, brackets D means the first D integers. We'll often use this notation. Brackets N as well will be the first integer. So there exists some subset of them that add to 0, such that this sum xi, I, and I. 0. Now, what we'll actually observe first is that this sum has to include You know what? This is doing very well if in the middle of proving something you remember the condition, right? I do need an extra condition in C, which is and D is even. Very good. It's not true, I think. I think maybe it could be one more if D is on. D is even. Good. Let's first prove then that this set I actually has to be everyone, has to be the whole of D. If I is not equal to D, then in particular, you can find some index which is in I, and you can find an index which is not equal. So if I have a subset, which is just some of the guys, then obviously you can find someone who is in I and someone who's not in I. Then there exists J in I, and there exists K not in I. So now what we can do is we can think about this inner product of this guy with xj and xk. And this will be really magic. Okay, so let's do the magic. What is the inner product of this with xj? When I've written 0 here, of course, I mean 0. Technically, I mean 0 vectors, right? But if I do an inner product of this with anybody, the answer is 0. So 0 is equal the inner product of xj and this big sum. But I can also calculate this using the fact that we're in an odd set, right? We're in this odd property set. Well, in fact, each guy with themselves has inner product 0 because we're in V, and with anyone else has inner product 1. So this actually gives you I minus 1. All these calculations are modulo 2, by the way. Because xj and xi will give you 1, because B has the odd property, for any I different from j, but we know j is an element of this set, so when you do that term, just get 0. So you pick up 1 for every element except yourself. And this is different from on I, right? Which is the inner product of xk with this sum. Because xk is not in the sum, k is not in I, then this has an odd inner product, has inner product 1 with everyone. And so you get everyone. But at the same time, this is still 0. Because the sum is 0. And so what we've learned is that 0 is not equal to 0. That is known as contradiction. And so And so we said here, if I is different from D, and we quickly got a contradiction. So it must be the case that I is D, and so I is D. And now what we do is we just repeat the first half of the argument from here, which is still valid because J is a member of I, everybody is a member of I. But as 0 still the inner product of xj with the sum, and this is still I minus 1, this implies, well, D is equal to I, so it goes D minus 1, which is equal to I minus 1, is even. That again is a contradiction because we remembered to put the condition that D is even in our statements. Very good. So this will be, well, there will be very important statements when we come to do the Ramsey stuff. C in particular will be related to the size of a clique you can find in a certain color. So this will be very important. Okay, let me just see. By magic, we have cleared the board, and we are ready to state the next lemma. So the next lemma will be about what kind of sets, how many sets of, with this totally isotropic property, this even property, all inner products even, how many such sets can you find in V? Okay, so we want to prove bounds on that number. So maybe you could say, let's, I don't know, Ti for totally isotropic, dl, this can be the number of L element totally isotropic subsets of Z2 from D. I mean, actually, if it's totally isotropic, in particular, you have to be contained in V. Right, so I could say in V contained Z2 from D, but they'll all be in V actually. And the lemma will say, look at these lovely bounds we can have on this. So lemma 1.2, let D be even and 1 less than or equal to L less than or equal to D, then the number CIDL, the number of L element subsets that are totally isotropic, is the most. Now we'll put bounds. These bounds are still quite big because there are quite a lot of choice. I'm not sure they're especially close to being best possible, but they're perfectly good for our applications. So you've got 2 to the DL over 2 plus D squared over 8 plus D over 4 plus 1. This is if L is bigger than D over 2. And if L is most D over 2, 2 to the DL minus L choose 2 plus 2. So let's see how you prove these bounds. So, yeah, given a subset, well, totally isotropic A contains Z to the end with L elements. We can sort of define its dimension to be the dimension of the subspace it generates, or in other words, the smallest subspace that contains A. So maybe to save space on the board, I'll say let rho be the dimension of the subspace generated by A. This just means subspace generated by A. It's the same as, yeah, the number of vectors you need to generate a space that contains A. Now, I really want to define this concept. You have a dimension associated with the set as well. Because, yeah, I just want to define that notion. Because now if you want to count the sets A, you can count them depending on this dimension, right? So how many of them have dimension 10, how many of them have dimension 20, how many of them have each dimension? Okay. As rho is the dimension of A, then what you can do is you can actually find rho linearly independent elements in A. And so we can list those first. We can imagine a sequence where you first list rho linearly independent elements of A, and then all the others are contained in their span. So then there is a sequence or an ordering, like an ordering, x1 up to xl, well, I'll say of A, of the elements of A, such that x1 up to x rho are linearly independent, and xi is contained in the set generated by x1 up to x rho for all I after that. So in rho plus 1 up to. So first you go out every time finding a new dimension, until at some point nothing else is linearly independent. Well, and then by definition, they're all contained in the space you've already generated. So we can use this to count how many of these sets have a certain dimension rho. How many ways are there to do this? Well, let me just put the question, how many ways? And then we can start doing calculation if you already know the question. How many ways are there to do this procedure? Well, the first, you have at most 2 to the D options. The second, you need to be in the orthogonal space. We need to be, right, because you can already, anyway, basically you reduce by 2 each time the space in which you need to pick the new vector. So it just goes to d minus 1, just d minus 2, down to d minus rho plus 1. And then all the remaining guys, actually I probably haven't been optimal in this. Maybe you could say d minus 1. Is it going to be in D? Anyway, it doesn't really matter. As I said, it doesn't really matter being super precise. Now, everyone else has to be in the space generated by first row vectors. So everyone else only has 2 to the row choices, right? The ends. And that's for all the other ones, you have L minus rho. And this quantity is 2 to the, here you have T occurring rho times, you have minus rho choose 2, And then here you have plus rho, L minus rho, and we'll actually give this a name, we'll call it theta of rho. So you have 2 to the theta of rho, where theta of rho is this expression. I think rho multiplies E plus L. Sorry, what was that? Rho, L minus rho. And from here, you'll get a minus rho squared over 2, but a plus of rho over 2. So put plus a half in here, and you have minus 3 rho squared. The exact value is not super important. I mean, what I'm likely to do now is maybe because it's more interesting to get onto the other part of the proof. Let's just say that you can observe that this function is increasing in rho up to the point where rho equals L. Okay. So basically taking rho larger works better. It's just that it's kind of, well, it's not quite calculus. If it was a continuous variable, you do calculus. You can just compare the value of rho plus 1 and rho, look at the difference. This is increasing all the way up to rho equals L. Of course, if L is bigger than d over 2, then what you do is you stop at d over 2, because it's impossible for a totally small isotropic space to have dimension bigger than d over 2 by the last letter, half b. So I think maybe we'll stop here, but basically what you do is you just sum these quantities, rho equals 1 up to L in this case, or rho equals 1 up to d over 2 in the first case, and it's always dominated by the last term. And you'll see that this expression is basically what you get from here if you put L equal d over 2, and this expression is basically what you get from here if you put rho equals L. Up to maybe a 2 or a 4 or something. You need to, basically the rest of the elements of the sum are less by, usually by a power of 2, and so it's a geometric series, and so it sums. You get just an extra constant. So now that we're armed with all these lovely estimates, we are ready to speak of the bound of Condon and Fermat. So maybe I'll go back over here and we can put it up. So theorem 3, and further, as I said, published in 21, I think. And okay, they did some other cases. They could also do these ideas in other finite fields, like Z3 to the D, and then they would use that to do a 4 coloring, or Z5 to the D, they'd use that to do a 6 coloring. So we looked at Z2 to the D, and we're going to do a 3 coloring. And for the way we're doing this and presenting in class, it makes sense to pick one nice example and just do that nice example, rather than try to make all the most general statements. So for the 3-color Ramsey number, diagonal Ramsey number, they prove a lower bound, which is 2 to the 7k over 8. You can put up to lower order terms or minus below k. Actually, I think you can put minus 5. Then it's just a fixed constant. So let's mention a few words related to the approach before we go into the proof for real. Well, this isn't really like a big overview. This is just like throwing some words at the board. But one of those words, you need to consider the properties of V. In other words, the things we've been doing today. We're going to need to know about, well, the idea of random colouring still. Let's go into random colouring. And the third thing we're going to do is at a certain moment, we're going to zoom in to a random subset. So again, it's not quite the simple idea of deterministic plus random. It's deterministic plus random plus random. We have two stages of randomness, and this seems to be something that comes up in quite a lot of applications. So, right, let's get down to details. Firstly, I guess we should decide, well, what are we trying to prove? We need to prove that if you take this value of n, you can find a 3 colouring with no monochromatic K. A small thing, you can easily check, say for K at most 10. I just kind of want to not start with nothing there. So assume K is at least 10. Another thing, you may have noticed in our results, we wanted to have K even, right? We wanted the dimensions to be even, and we're going to be using K as the dimension. It's useful if K is even. So let's just prove this result with -4 if K is even, and then it holds to the odd K just by monotonicity. Right? Because if you avoid peaks of size 10, you also avoid peaks of size 11. So it suffices to prove even K is 10 if we put n is 2 to the 7k over a minus 4, then there exists 3 colouring of Kn with no monochromatic. What's for mono? No monochromatic. So that's what we need to prove, right? So what will this colouring be? Well, it's interesting, isn't it? We need to know what the colouring is. We also need to know what the vertices are. And what we do is we start with the vertices being the vectors in V. Remember that set, the even vectors, the isotropic vectors, in Z2 to the K. The dimension is the same as our K. So let V contained in Z2 to the K be, we'll say V as before, the set of even vectors, isotropic vectors. And we're going to colour all of the pairs in V. Now, V will not be our final vertex set, because at the end it will be useful to zoom into a subset. So, colour, let's do the colouring now. If you take two vectors x, y, and v, we're going to colour x, y green if their inner product is 1. Otherwise, in other words, if your inner product is 0, colour. Now we do randomness. We do red or blue, independently of property and half. Red or so many pens to be done this funny trick of writing colour. Colour red or blue, as usual, colouring the edge red or blue, independently of property and half. So is it clear the colouring? We use this structure coming from the inner product to colour, in fact, it's like half the pairs, right? Colour half the pairs green, but in this very structured way. And then the other colours, the other rows to colour them red or blue, kind of with the airbrush in it. So, what can you tell me about the green subgraph? If I take any subset of V with k vertices, what would happen if I had a green clique? Then I would exactly have a set of size k with that odd property. And that's impossible because k is the dimension of the space, and then it was part C, right, of that lemma, so that is impossible. So there is no green KK. So already one colour is sorted. We're very happy. The other two colours we still have to deal with, but obviously they're going to be completely symmetric. So in a sense, we're just down to sort of dealing with one colour, right? In a way. If you want to show it's unlikely you have a red clique, because if it's unlikely you have a red clique, then by symmetry it's unlikely you have a blue clique, and it's all going to be good. But is it all good? No, it's not all good. If you do the calculation at this point, you will find that you would expect to have lots of red cliques of size 10. So in fact, it's too ambitious to do this using all of the vectors in V. Think of this has 2 to the k minus 1 elements, and we're only claiming a lower bound 2 to the 7/8 scale. So what we can do is choose a random subset and just zoom into those vertices, and just say we're just interested in the colouring in here. So let's do that now. Let P be 2n over the size of V. We actually know the values of n and V, so I can actually write P as an exact thing. So I guess 2n would be like this, minus 3. So 2 to the 7k over a minus 3. And then this k minus 1, right? So minus k minus 1. In other words, P is 2 to the minus k over 8 minus 2. Anyway, the exact value of P is not really what matters. What matters is if we do a P random subset, if we put each vertex in P independent property with this probability, the expected size would be 2n. Right? You'd actually have a binomial distribution of the size of the subset with mean 2n. And it's just an easy property of binomial that, well, it has roughly probability half of being at least its mean. Right? So it certainly has probability at least a half of being at least half of its mean. It's not, you could easily prove this with Chebyshev or Chernoff. So I'll just say note. Well, okay, let's first say let U contained in V be obtained putting each vertex in U property P independently with probability P. And I'll just say note, U has size at least n with probability at least a half. You know, if K is large, this would actually be like convergent to 1 and all that stuff. But this is enough for what we need, because when you just need existence, it's going to be plenty as long as the probability of a clique in the other colors is small enough. Right, so now we need to do some kind of first moment calculation about the number of cliques in one of the other colors. So that X be the number of red KK. And what can you tell me about the expected value of X? Now, what do we think? How can we calculate the expected value of X? So we can ask, what do we need to happen? What sequence of events needs to happen in order for, you know, say a set of size K to end up all being red?
And this is that all coloring is already fixed.
Or what's that?
And this step all coloring is already fixed, right? Just
Yeah, the coloring was, yeah, the red blue bit was random, right? Actually, maybe let me just do one thing before the expected value. Let's do one thing first, which is maybe the question I wanted to ask you really. If I fix A contained in V of size K, well, one thing that you need to get a red clique on those vertices, you need there to be no green. If there's green, then green is red. So it's necessary that you never have an inner product that's 1. In other words, it's necessary that A is was it totally I always forget the isotropic, right? So let's fixate with these 3 properties. It's contained in V, has size K, and it's totally isotropic. What is the probability that A is monochromatic in red? So if you put it totally isotropic, you've already saved it from green. It's no green. What else needs to happen? Well, I said it's monochromatic in red in the coloring restricted to U. Because our wells at the end of the day is just going to be U, right? Nothing. So in order to be a monochromatic red clique in U, you need 2 things to happen. You need that every edge is colored red when you do the random coloring. And you need that all the vertices are put into U. So P to the K. And I think you can do some calculations here with the powers of 2. This is minus K squared over 2. When I started doing it, I noticed you could just do a constant. So when I did the calculation, really you should just say throw away everything that's below K squared. But for some reason I just did the calculation and then I thought it seemed fun. But maybe it's a bit of a mess. Right. So your p to the k gives you minus k squared over 8 minus 2k. So this is the probability that A is monochromatic and in U. So now we're nearly finished. We just need to combine that bound with our control on the number of totally isotropic sets, right? So now the expected value of X is the sum over the expected number of sum value of X is the number of red KK we get in U in the end. So it's the number of these guys times the probability of colour them red. But we have a bound on the number that was about, in that case, it gives 2 to the 5/8 k squared plus k. So let me put that here, 5/8 k squared plus k. This is choices of A, or an upper bound of the number of choices of A, by lever 1.2, and we have this probability, right? So I think we have minus 5/8 k squared, and we have minus 3k over 2. And these will cancel, except you have 2 to the minus k over 2, which is less than 2 to the minus 5 or something. And so the expected number of red cleats is most 2 to the minus 5. The probability you have a red cleat of size k then is at most 2 to the minus 5. The same works for blue. So the probability in these a half minus, I guess, a 16th, which is like twice like this. We have the set we've restricted to U has size of least n, and the 3 colouring of U contains no monochromatic KK. Right? Remembering, you couldn't have a monochromatic KK, you couldn't have a green one, because that was just impossible by linear algebra. Probability of having a red one is the most 2 to the minus 5 by this calculation, and similarly for blue. So it's a nice combination of using those algebraic facts and using random methods, 2 different random methods in this case, a random colouring of those pairs when the inner product is 0, and zooming into a random subset, because you can see if you didn't do the random subset thing, then you just wouldn't have enough factors to cancel here, you wouldn't get the result, you'd have too many points. So this is the bound that Conlon further managed. I suppose we need to see and think if we actually have time today for big stuff. Maybe I should say something about that in the next class then. Right, so maybe I'll stop for now in terms of, and then, yeah, so we'll carry on in the next class and still say something about the lower bound of Biggerson. We'll also say something about upper bounds in 2 colour, and it'll probably be, well, next week we'll get on to the